Stanford University.
Okay, back to thermodynamics. Now, when I was going through my lecture notes for tonight, I realized just how subtle some things can be, and really why it is that students' eyes go like this when they're studying thermodynamics. It is full of all these fancy calculus tricks with sometimes very little intuition about what's really going on. But it's really all in the calculus tricks. We're going to study tonight a particular, and only one problem. We're going to study the problem of pressure of an ideal gas tonight. Now, intuitively, we know where the pressure comes from. It comes from the molecules bouncing against the walls of the system. We could calculate it just by estimating we've already calculated the average energy of every molecule. It was a 3/2 kT, 3/2 the temperature. So we know how fast they're moving on the average. We can estimate how many of them are moving in each direction because they're pretty isotropic. You might wonder, incidentally, if the molecules near the wall are isotropic. After all, the presence of the wall influences what's going on near it, and you might think, well, maybe there are more going horizontal to the wall than going parallel to the wall and going the other way. Turns out not to be true, that even very close to the wall, the distribution of velocities is still pretty isotropic. But you might wonder whether that's a principle or just an accident. You might also wonder whether the velocities near the wall happen to be different than the velocities in the interior far from the wall, in which case you'd be making a mistake by just taking the good old 3/2 kT and using it for every molecule no matter where you are. Turns out you're not making a mistake. But how do you know you're not making a mistake? You know from statistical mechanics. You know from an honest evaluation, an honest set of principles which don't use intuitive pictures of molecules hitting the wall and so forth, but which really use the basic foundations of statistical mechanics. But the foundations of statistical mechanics are mathematical. They're very mathematical. They're not hard, but they're mathematical. And as I sort of emphasized to you over and over, in situations where the rules are mathematical and when you purposefully give up intuition, because you're not sure that your intuitions are correct, such as, for example, that the velocity distribution near the wall is the same as in the interior of the wall. So you purposefully give up intuition and you ride the mathematics. When you're riding the mathematics, the rules are sort of these autopilot rules where you first figure out what you want and then you just start going with it, using whatever tricks you have until you suddenly find yourself with a formula that you recognize. And that's just the way it is. You get good at it after a while. And the great physicists that I know all were very good at it. And I don't mean people who just studied statistical mechanics. I mean all of the very, very good physicists I know somehow love thermodynamics. Why? It's fun, but it's the fun of surprises. It's the fun of surprising relationships which suddenly fit together and tell you some physics. That's what the attraction is for many of us. Einstein was the grand master of thermodynamics. Feynman was a grand master of it. I'm a grand master of it. Well, maybe. It's good stuff. Anyway, yeah.
In the end, when you finish your mathematics, when you've written the mathematics, can you check it with your intuition? It's kind of tempting to see, does that make sense?
What you're really doing is checking the intuition, not the mathematics. I mean, it could easily be wrong that the distribution of velocities near the wall is the same as in the interior. You don't want to rely on that. You don't want to go through all of the mathematics and then say, well, I think I've proved that the rules of calculus work out okay because they agree with my naive intuitions about the way molecules behave near the wall. It's the other way. You're checking your intuitions from the mathematics. Okay, so we could do a little calculation of calculating the pressure on the walls, given that the average velocities of every molecule is 3/2 kT. We would probably do the calculation by saying, let's not even talk about averages. Let's say this room is filled with molecules which are moving with velocity 1/2 mv squared equals 3/2 kT, right? Let's just say 3/2 temperature. Use our favorite units that don't have Boltzmann's constant in them. We know the mass of every molecule, therefore we know the velocity of every molecule. When we know the velocity of every molecule, we can compute the force on the wall by asking how many molecules per unit time hit the wall. If indeed they're distributed uniformly, which we don't know for sure, and if we know that their direction of their velocities is isotropic, we can calculate the number of collisions on the wall per unit time. We can calculate the momentum delivered by each particle to the wall. The particles bounce off the wall, and the perpendicular component of momentum, which is originally going this way, is then going this way. We can calculate the momentum delivered to the wall, and of course, force is rate of change of momentum, and so we can calculate the force on the wall. The pressure is the force per unit area, and so we can calculate that. It's fun. You can try to do it yourself, and you'll get the right answer. You'll get the right answer in the case where the molecules are completely free and so forth. But that's not really good enough. We really want a set of rules which are good enough that they could take into account collisions between the molecules. My God, collisions between the molecules, they could upset the whole thing a lot, and they do. And they do. We want a set of rules which is robust and which doesn't depend on the detailed, oversimplified, supersimplified model of a free gas. A free gas means a gas of particles where the particles are not interacting with each other, the ideal gas. So the ideal gas is a place that's easy. It's easy to do things with, but it's not very general. The rules of statistical mechanics are very, very general and would be sufficient to calculate if you can do the calculations. If you can do, then you can calculate the relationship between the pressure and other variables very generally. What is it that we want? We want something called the equation of state. We would like to calculate or know what the pressure is as a function of temperature, volume, but what is it that determines the gas in this room? Basically the temperature. That's about it. There's also the number of gas molecules. Well, there's also there's the number of gas molecules in the room, number of molecules, temperature, and possibly the volume, but it won't depend on the volume. Well, yeah, no, sorry, it will depend on the volume. Depend on the volume. We would like to calculate the pressure in terms of those things. So we need a theory. We need a set of principles. We're going to describe those principles tonight and work out, I hope, the pressure of an ideal gas. With no intuition whatever. No picture in our minds of what we're doing. I'm not saying that pictures in your minds aren't good things for understanding physics, but there are times when you want to suppress the pictures and simply go with the mathematics. And this statistical mechanics is one of them because you want your rules to be general. Okay, let me just remind you over here on this blackboard of a couple of a fact, mathematical fact that we worked out before. And then I want to prove a little theorem. This is one of the damn trickiest theorems. It drives people crazy. It drove me crazy, and I proved it once when I was a young man, and then I come back to it every time I teach this subject, and every time I teach the subject I cannot remember how you prove it, and I have to sit with a piece of paper for a half an hour until I find, and it's a very, very simple theorem. And then we'll use those theorems to calculate the pressure. But I want to get to some mathematics on the blackboard first, just so we have them. And I'll try to remember not to erase them so that we'll have them when we need them. Please don't let me erase. All right, the first thing had to do with entropy. And entropy is the summation, you know what it is, summation minus the summation of p log p, p sub I log p sub I. And if the distribution is the Boltzmann distribution, it's minus the summation. Now p sub I is 1 over the partition function, e to the minus beta times the energy of the ith level, that's p sub I, and then logarithm of p sub I. So what's the logarithm of this object here? It's minus beta e sub I, the logarithm of this one, minus log z. All right, so everybody recognizes this. This is a product. The logarithm is the sum of the logarithms of the two factors in the product. So that's minus log z, minus beta e sub I. Minus signs cancel. Might as well get rid of them now so that we don't make mistakes later. And then if you remember, the first term here is just beta times the average energy. Probabilities for I times E sub I, when summed, is just the average energy. So the first term just gives us beta times the thing we've been calling E, the average energy. Okay, so let's get rid of it. We got it. Now let's get the second term here. Well, it's times log z. All right, we have this sum to do here. Z and log z don't depend on I. Right? What depends on I is only this minus e to the minus beta I. What is the sum of e to the minus beta I over I? It's z. That's the definition of z. So the z that you get from the summation cancels the z over here, and all you get is plus log z. That's the entropy. N log z? What is n?
Well, you have a summation summing a bunch of terms that are 1.
What's 1? The summation of e to the minus beta e is z.
Right.
Cancels the z in the denominator. Okay.
It's easier to see if you keep the first part of that summation just as p of I rather than expanding it out.
Mm-hmm.
Yeah, that's true.
Right. Okay, let's just rearrange it a little bit into a sort of standard form. This is the formula. This is the formula. Let's remember that beta is 1 over the temperature. And okay, so we have S. Sorry, 1 over. What did I do? This was beta E 1 over temperature. Okay, right. So let's multiply it by temperature and write the formula in the following fashion, only because this is sort of standard. Energy minus T times S. Energy, is it energy minus? Yes, I think it's energy minus T times S is equal to minus T log Z. I've multiplied by T, so that means we have T times S. We get rid of the T in the energy term, energy minus T times S, and that's equal to T times log Z with a minus sign. I think with a minus sign. Yeah. Yes, with a minus sign. All right, this thing has a name. It's not important what its name is. Well, it's important only because you may want to be using it over and over. If it occurs over and over in physics, we'll want to give it a name. For our purposes, we really just want this formula here. This is the important formula here that we're going to use. Okay, but we might as well give this its name. First of all, its name is A, and it's called the Helmholtz free energy. Things are given names when they occur over and over again. We're going to find out that it plays a leading role in calculating things like pressure and all kinds of other things. Okay, so this is called A. And it's another thermodynamic variable. We have energy. What do we have? We have energy, we have temperature, we have entropy. And we now have a new thing called the Helmholtz free energy. Helmholtz, H-E-L-M. H-O-L-Z. And at the moment, it's simply an object which has occurred once and therefore not very interesting. We're going to see it occurring once more tonight, but I tell you that it occurs all over the place. Okay, that's one piece of information that we'll need. In this form, we don't need the fact that it's called A or that it's called Helmholtz free energy. We need this equation. The next equation, this is not the theorem which drives me crazy. The theorem which drives me crazy, what we're going to be doing is introducing yet another variable into the problem. I call variables of this kind control parameters. In the notes, you will see something about control parameters. Control parameters are parameters that you, as an experimenter, easily can change. They're parameters which are macroscopic. They're not trying to change details of one molecule at a time. And an example would be the volume of the container of your gas. You could have a piston. You could have a cylinder of gas with a piston in it, and and move the piston back and forth, and in the process change the volume of gas. So volume is a control parameter. Other control parameters: magnetic field on a system, the electric field on a system, or applied electric field, applied magnetic field. I don't know. Can you think of any others easily?
Density, pressure?
No. Pressure, we're going to see the relationship. Yeah, you can, but variables come in pairs. One is usually called the control parameter, and one is called the conjugate thermodynamical variable. Pressure and volume are closely connected, and they're conjugate pairs. Yes, you can change the pressure. You can have a pressure gauge in here, and by moving the piston, change the pressure. But, of course, what you're doing is changing the volume, and the response is a change in pressure.
Are you assuming that all the molecules are the same? So there could be
Absolutely not.
different gases.
We're not even assuming it's made of atoms, whatever it's made out of. But, yeah, we're not assuming that it's a gas. Could be a liquid, could even be a solid. Could be a solid in here, and we'd be squeezing on the solid. That's why it's important to have general methods. You cannot use the ideal gas law for a solid in there.
Well, what I was thinking was that you were changing the amount of material inside.
Yeah, that would, you could change the number of molecules. Yeah, that's a control parameter. Right. Okay.
You have like steam and condensed water. You have two states.
If they happen to be in equilibrium, there is a temperature. If you're at the boiling temperature exactly, then you can have steam and water in there simultaneously. Yes. Yeah. So it's not even a gas. It's neither a gas nor a liquid in that situation, right? And if it was in a gravitational field, the liquid might sit on the bottom, and the gas might sit on the top, but it would still be thermal equilibrium, and you could still study it by the methods we're going to be using. Okay, so let's. I'm going to write down. I want this theorem, just because we're going to use it. So let's put it on the theorem blackboard over here, or our. I don't know whether it's a theorem. It's too simple to be a full-blown theorem. But here is what it says. Supposing you have two functions of two variables. That sounds complicated. One of the functions we're going to call E. It will be the energy later. And the other function we're going to call the entropy. S, we're going to call S. And these two functions are functions of two other variables. Namely, remember, energy, entropy over here, two other variables, the independent variables in the problem, and those we're going to call T and V. There's no significance to the way I'm lining them up. Just think of these as the independent variables that we can control from outside, the temperature, if we like, and the volume. So those are independent variables, and given the nature of the system, given the nature of the gas, whatever it happens to be, given the temperature and the volume, the dependent variables, the ones that if you knew enough you could calculate, would be the energy and the entropy. Those are the two variables. Now, somewhere's in there that might, yeah, those are the things that we're interested in. All right, the following theorem. You're going to hate this theorem because it's going to be totally unintuitive, and you're going to ask, what's it good for? Looks like a silly theorem, but here's the theorem. And it has nothing specific to do with the particular nature of these functions, of what they are. Two dependent variables, two independent variables. Okay? It says, the theorem says that the derivative of the energy, or E, the derivative of E, with respect to the independent variable V, at fixed S. Now that's a funny thing to do. If these are the independent variables, you usually differentiate the dependent variables, keeping some independent variable fixed. But we're going to do something different. We're going to differentiate E with respect to volume, keeping the entropy fixed. We'll see what that means in a moment. Okay? That's what we're interested in. And that's the sum of two terms, or actually the difference of two terms. One of them is the derivative of the energy of E with respect to the volume, keeping the temperature fixed. Well, that looks a little more normal. We're differentiating a dependent variable with respect to an independent variable, keeping the other independent variable fixed. That's what we normally do in calculus. But there's an extra term here, and the extra term is minus the derivative of E with respect to the entropy at fixed volume which is another little weirdo, calculating the derivative of E keeping S fixed. Calculating the derivative of E with respect to S, keeping the volume fixed. That's another weird thing. And then the derivative of S with respect to the volume, keeping the temperature fixed.
Plus or minus? Plus or minus?
Minus. Yeah.
Or multiply? Multiply.
Sorry, where?
The second term is the multiplication of the first.
Oh, this is multiplying. Multiplying, yeah. Yeah, this is a really weird, totally unintuitive, and I think if you sat down to try to prove it, you'd probably wander around in the dark for quite a while. So it takes me, I would say it takes me a half an hour on a good day to remind myself what this means, how you prove it. Do you want to see the proof? It's a lovely little proof. Yeah. I like it so much because I figured it out myself. You sort of fall in love with those little things that you figure out yourself when you're young. But I think I could still do it now. In fact, I did do it now. I did it this afternoon. All right. Let's draw our independent variables. Let's hope I can do it now. Temperature and volume. Or T and V. Okay? Now, there are two dependent variables. One of them is called S. Let's draw the contour lines of S. But I'm only going to draw one contour line. I'm going to draw some specific line along which S is constant. I don't know if it looks like that or not. I'm just drawing a line. There's S. S is equal to some constant. Of course, there are other contour lines, but I'm not going to bother drawing them. There's one contour line. That's S equals constant along there. That's fixed S. That's the important thing. That's fixed S. And we want to calculate the rate of change of E, that's another variable, with respect to volume. In other words, how fast E is changing as you change the volume, but along a line of constant S. That's what this says. Keeping S constant. So here we are, we're at a point over here. We're going to change the volume to go to a point over here. And we're going to stay on a line of constant S. So along that line of constant S, we're calculating, if you like, delta E by delta V along that line of constant S. I use the notation delta E and delta V because I like to remind myself that these things are actually ratios of differences. All right. Now, let's write down the following formula. When I'm using delta E, I'm not distinguishing it from dE. It's infinitely small. It's a differential. It just helps remember what you're doing to remember that they're ratios of small differences. So delta E is partial of E with respect to volume at fixed temperature times the change in volume. And moving from any point to any other point, the rate of change of E with respect to V at fixed temperature times dV plus dE by dt at fixed V times delta T. All right, what these are, if you like, these two things are, the first one is the rate of change of E with respect to V, keeping the temperature fixed. In other words, it has to do with moving from here to here. And the other one is the rate of change as you change temperature, keeping volume fixed, keeping V fixed, times delta T.
Isn't that the usual definition of partial derivative?
Yeah. This is perfectly normal. Nothing special yet. Okay. Now, the first term here is the first term over here. It's this second one that we want to manipulate and fool around with and see if we can understand why it's equal to this. All right. So there's two steps. The first is to write that the rate of change of E with respect to t, let's move it down on the blackboard, give it some more room, plus, what did I have? The E by dV at constant, what did I do? Sorry, the E by dt at constant V times delta t. All right. The first thing we're going to do is write. Now, all of this is justified. You know, you can, at any given point, you can start playing in any number of different directions, manipulating various things. And so the process is a sort of branching tree of possible formulas that you can write. Well, fortunately, it's not that big. And if you're lucky, you'll hit one along that tree somewhere that says, ah, I noticed something good. And I'm really afraid that sort of is the way it is. Eventually you get good at it and you get an instinct for what to do next. All right, so the E by dV, let's just look at this. We have on here dE by ds at constant volume. But this is dE by dt at constant volume. So think of the volume as fixed, and the E by dt at constant volume is the same as the E by ds at constant volume times ds by, I forgot what I had here. I had the E by dt, right? Yeah, I had the E by dt. So ds by dt also at constant volume. Okay, so here I have my dE by ds at constant volume. Oh, let's do one more thing now. Sorry. We're interested in the rate of change of E with respect to V. That means we should divide by delta V on both sides. We should get rid of the delta V, divide it by delta V, divide it by delta V. Okay, so now we're cooking. But where so far have I put in that I've moved along a line of constant S? I haven't. Nothing in here has told me that I'm moving along a line from one point to another, along a line of constant entropy. Now, why we're interested in constant entropy will come out. Not from this formula, but it will come out soon enough. So, good. Okay, so we're moving along this line. How can we characterize this line? This curve at this point is characterized by a slope. That slope is just delta t by delta v. Let's see what we can figure out about it. Let's use a little bit of calculus to see if we can work out something about delta t by delta v. So, let's write down the condition that we're moving on a line of constant s. That means along this line, ds is equal to 0. Along this line, ds is equal to 0. And now, all we have to do is write that ds is partial of s with respect to volume at fixed t times d volume, delta volume, plus partial of s with respect to t at fixed volume times delta t. But along this line, ds is equal to 0. Right? ds is equal to 0 along this line. It's the definition of the line. So let's make this equal to 0. And now we're going to be able to get a formula for delta t by delta v in terms of these partial derivatives. You see where I'm going? All right, so let's divide by delta v, because what we want is delta t by delta v. So let's divide by delta v. Here we have our target over here, delta t by delta v. And we can now immediately read off that delta t by delta v is equal to minus ds by dv at constant t divided by ds by dt at constant v. This would be true for any function s whatever on this map here, that the slope of the contour lines, this is the slope of the contour lines, is related to certain partial derivatives. I don't know if it takes me a minute or two to see why this is. I have to go through this little step here to see. But now we know what delta t by delta v is. So let's put it in. It first of all gives us a minus sign. Okay. And then delta t by delta v is partial of s, let's write it out, partial of s with respect to v at constant t divided by partial of s with respect to t at constant v. All right, so we have 4 factors in there. 4 factors, 3 in the numerator, 1 in the denominator. This is in the denominator here, the ds dt. But fortunately, by a great stroke of luck, the thing in the denominator happens to be the same thing as one of the terms in the numerator. All right? So, again, as I said, we could have gone off in all sorts of random directions, but this direction seems like a good one because this thing is getting simpler now. So let's get rid of the numerator, sorry, the denominator and the numerator. And we're done. Well, we're done. What have we done? What have we done? We've proved this little lemma here. Okay. I cannot prove this lemma without drawing this picture. It's something you ought to be able to prove just by mechanical steps, but I cannot prove it without drawing the picture and then figuring out what I'm doing.
Can I ask a question, please? When in order to reduce, we have to be sure that the derivative of entropy to temp with respect to temperature constant V is not 0.
Yeah.
Do we know that?
For most systems, in most circumstances, yes. There are some special cases where it's not true, and then you'll have to be more careful. But generally speaking, yes, entropy is a monotonic function of temperature. And the reason is simple. The Boltzmann distribution, as you change the temperature, if you increase the temperature, it gets narrower. As you decrease the temperature, it gets broader. And entropy is just a measure of that width. So typically, yes, there's some very special cases, but yeah, you know, things are nicely behaved as a rule. Okay, so here we have our 2 facts. The third fact has to do with the definition of pressure, and I want to make very clear that pressure is just one special case of a response to a control parameter. I'll show you what I mean by a response to a control parameter. So I was going to say one thing we have to do, but actually 2, but they're easy. The first thing is to understand what pressure really is. Here's our cylinder. Here's our piston. The molecules in here are hitting the piston and so forth, exerting pressure on it. Supposing we move the piston a little bit. The pressure in the interior does work on the piston. Okay? If we move the piston out, the pressure pushes out and does work on the that work. Where does that work come from? That work is energy. The work done on the piston is equal to the change, an opposite sign. If the gas does work on the piston, then there's a change in the energy in here of negative sign. Okay. I'll tell you what, maybe it's smarter to put this upright in the following way, and you can think about it. Yeah. Imagine the piston rises a little bit. Well, that means there's been an increase in the energy, in the gravitational potential energy of the piston in this case. All right? That's called the work done on the piston, okay, by the pressure. And by energy conservation, any work that's done on the piston must be taken away from the gas. So energy conservation tells us that the change in energy of the gas is minus the work done on the piston. Now let's suppose that the area of the piston is A, and let's suppose that the piston is moved by an amount dx vertically. Move dx vertically, then, and we also have to imagine something else. We have to imagine, first of all, that we do this slowly. Some odd things can happen if you do it fast. For example, you could pull a piston out so fast that no molecule has a chance to hit the piston as it's moving. Then during that period, there'll be no pressure on it, okay? That's a rather extreme situation, but it does illustrate for you that you want to define pressure by being able to average over many collisions. So you want to slowly move the piston, slow motion, in the limit of very slow motion. And there's something else you want to do. You want to make sure that no energy comes into the system from outside. In other words, you want to insulate the walls of the system. Okay. I remember when I was an undergraduate, I learned the word adiabatic. I had no idea what it meant, but my professor of engineering told me that it means that a system is insulated from heat coming into it or out of it. And then later on, when I was in graduate school, another professor told me adiabatic means slowly. Well, what adiabatic means is slowly and no heat comes into the system. Okay? If you move the piston adiabatically with no heat coming into the system, and the change of the energy of the gas is minus the work done on the piston, and minus the work done on the piston is the force on the piston. That's the pressure times the area. Pressure times area, that's force. Pressure times area is force. That's the definition of pressure. Force per unit area. That's force times dx. And area times dx is the change in the volume of the gas, right? Area times dx is the change in the volume, so we can write A dx as dV. This is what's true, and this defines pressure. It defines pressure. In fact, here's the way we can write it. We can write it that it is the change in energy with respect to volume. The only question is, what do we keep fixed in doing this derivative? What do we keep fixed? It's some rate of change of energy with respect to volume under the circumstance that we do the operation adiabatically. Okay. Now, there's another aspect of the notion of adiabatic. Anybody know another meaning to adiabatic?
No change in entropy.
The second law of thermodynamics, which we will come to, says that entropy always increases except when it doesn't. When it doesn't increase, it stays the same. It never decreases. Okay. Never say never, but never mind. Okay. What are the processes where the entropy doesn't increase, where it stays the same? Those are the adiabatic ones. So let me explain to you. I'm going to explain it to you from a quantum mechanical point of view. And the only aspect we're going to use of quantum mechanics is that energy levels are discrete. Nothing else. In other words, the E, there they are, E sub I up there, definite energy levels. So we have our box of gas, and here I'm going to plot the energy levels, and it has a collection of energy levels, a collection of possible energies that the gas in the box can have. Not the single particle energy levels, the possible energies of everything inside the box. There's some discrete collection of numbers in quantum mechanics in any case. Now we're going to change the volume. We're going to change the volume, and what happens to the energy levels? Do they stay the same? No. Why should they? If you want to calculate the energy levels, you have to solve some problem, some Schrodinger equation, whatever. And the Schrodinger equation depends on the size of the box, and the energy levels change. Actually, I've got it right upside down. As you increase the volume of the box, the individual energy levels surely go down, but it doesn't matter because we're just being general. We could imagine a situation where the energy levels go up. It doesn't matter. All right. Now, what is true? Now, this is something that I'm not going to prove for you. It's a quantum mechanical theorem. It is called the Adiabatic Theorem. And what it says is that if a system has a definite energy and you slowly change the parameter, in this case the volume, whatever control parameter happens to be, if you slowly change it, the system will stay and simply ride along the energy level, keeping not the same energy, but it won't jump from one energy level to another. It will simply stay, if this is the 500,037th energy level, the system will stay in the 537, whatever I said, whatever the number is. In other words, the energy levels will be remembered, and if it started here, it will be here. If you change a system rapidly, this is not what happens. If you change a system rapidly, you can have jumps from one energy level to another. That's what's special about adiabatic. If you go slowly, the energy levels, the value of the energy changes slowly, but you don't jump from one to another. That means if you started out with a collection of probabilities, P sub I, labeling the probabilities for different energy levels, the P sub I stay the same. The value of the energy may shift, but the probabilities don't change. If there was a probability, let's say 0 everywhere except for this particular energy level, well, you'll still have 0 everywhere except for the energy level over here. If you have probability a half here and a half here, it will remain a half and a half. So while the energies change, the P sub i's don't. And the entropy is just built from the P sub i's. It doesn't care what the energies are. If you have a probability distribution, then S is equal to minus summation I, P sub I log P sub I. And if all the probabilities stay the same, then you can be sure that the entropy stays the same. That is why an adiabatic process is also sometimes called an isentropic process, meaning to say that the entropy doesn't change. That's the general definition of adiabatic. Okay? No change in entropy. Now, of course, slow would not be good enough if you could put heat into the system. If you put heat into the system, well, that's corrupting it and changing the system, changing the energy. That's not what you want to do. Adiabatic means slow with no added or subtracted heat. And under those circumstances, adiabatic also means constant entropy. So now we know what to hold fixed in this formula. The change in the energy with respect to volume, holding the entropy fixed. Well, that of course is the reason that I went and that's the reason we spent a little bit of time on a formula up there. This formula is good enough. But it's kind of hard to calculate things at fixed entropy. You have to figure out what you're usually provided with. The easy thing to calculate is things at fixed temperature. You stick in the temperature into the Boltzmann distribution and you calculate, and what you get out is an answer which depends on the temperature. The easy thing usually to calculate is how things vary with temperature, just because the temperature is a thing which directly appears in the Boltzmann distribution here. So it's always easier to work as a function of temperature than as a function of anything else. So what we'd like to do is to convert this to something that involves derivatives with respect to temperature instead of entropy, and then we can go back and see what we can learn from the Boltzmann distribution. Okay, so here we have that this is equal then to the derivative of the energy with respect to the volume at fixed temperature. In other words, holding fixed the temperature in the Boltzmann distribution, minus, I'm going to rewrite this, minus the derivative of the entropy with respect to the volume at fixed temperature, times the derivative of the energy with respect to entropy at fixed volume. Now this looks terrible, looks too complicated, but fortunately this is something we've seen before. Anybody remember what dE by ds is? The temperature. Holding the volume fixed. Holding the volume fixed means you're holding the system fixed. You're not changing the control parameters. It's just the original system with fixed energy levels, and you're holding that fixed. Under those circumstances, dE by ds is just the temperature. Remember, that's dE equals T ds. dE equals T ds. Or dE by ds is the temperature. So this is not quite so bad. We can replace this factor over here just by the temperature. It's getting simpler.
Do we have a negative sign for pressure?
Yeah, from here. Thank you. Now the only derivatives are derivatives with respect to volume at fixed temperature. That sounds promising. Volume and temperature can be thought of as independent variables, and the only derivatives that appear are sort of familiar things, how the energy changes with respect to volume at fixed temperature, and how S changes with respect to volume at fixed temperature. T, that's just the temperature. One more step. This also happens to equal minus the derivative with respect to the volume at fixed temperature of the energy minus T times S. Okay, the first term you can see, dE by dV, that's dE by dV at fixed temperature. The second term, if I differentiated with respect to volume at fixed temperature, I would get two terms from the product here. One of them would be T times the derivative of S with respect to the volume. That's this one. What's the other one? The other one is derivative with respect to the volume of the temperature at fixed temperature. How does the temperature change as you vary the volume if you keep the temperature fixed? It doesn't change. Right. So the second term isn't there. And now we have our fundamental theorem that the pressure is equal to the derivative with respect to the volume of the Helmholtz free energy at fixed temperature. Now, that is much simpler than anything else you could imagine for the pressure. And in fact, we know a little more. We know that the Helmholtz free energy is just minus T log Z. So if we can calculate the damn partition function, we're sort of finished. So let's write that again. I think it's plus now. This will be plus the derivative with respect to the volume. This is at fixed temperature, so we can take the temperature on the outside. We don't need the plus sign there. The temperature times the derivative of log Z with respect to volume at fixed temperature. All we need to be able to calculate is how the partition function depends on the volume, and we can calculate the pressure. Everything I've done up till now is completely general. It wouldn't matter if it were a liquid, a gas, a plasma, or a solid inside the cylinder. Doesn't matter what the chemical composition is. This is what statistical mechanics, not kinetic theory. Kinetic theory is this intuitive picture of molecules bouncing around. This is what statistical mechanics says. Pressure is equal to temperature times the derivative of the partition function. Now you can calculate, you can carry this out for basically any control parameter. I just used volume as a control parameter because it's familiar. For any control parameter, there is always a derivative of energy with respect to the control parameter at fixed entropy. That is called the conjugate thermodynamical variable. Volume and pressure are conjugate variables thermodynamically. There are many others. I'm not going to go into them now, but anytime you have a control parameter, then you can ask how the energy of the system depends on the control parameter at fixed entropy, and that defines another variable which is like pressure, which plays the role of pressure. All right, but let's now that we've... This is going faster than I thought. I thought this was going to take a long time. Oh, okay. Yeah. In other words, there's one point. You see the power of defining, it's not that I was saying, you see the power that this quantity potentially can have. It just appears all over. Do you remember another thing that that log Z depended on? No, not that depended on log Z. The derivative of log Z with respect to beta was the average energy. Log Z has a lot of stuff in it. Okay, when you know log Z, you know a lot of stuff. All right, so, Gary, you wanted to ask a question.
Yeah, it has to do with sort of the adiabatic thing. It seems that this principle is a constraint that's throughout thermodynamics. What happens if you do not do if you don't use if you move a piston quickly and it's not an adiabatic movement, you have a potential energy component to it? That's the only difference, isn't it?
No. Then it becomes a complicated non-equilibrium process. I just gave you an example. If you move it fast enough, no molecule will hit the wall. There won't be any pressure. But of course what will happen is you've made a very sudden change, and how will the system respond? The system will respond by a shock wave going through the fluid. You know, imagine that you had a fluid and you suddenly, it's easier to think about if you suddenly squeeze the fluid. You can change the volume in either direction. You suddenly squeeze the fluid and you make a shock wave going through the system. You'll also make a shock wave if you pull it away, and very complicated things happen. And it's not controlled by simple statistical mechanics. It's controlled by the whole dynamics, the whole non-equilibrium dynamics The only thing you can be sure of is that the entropy increases. Now, you can actually work out, for the special case that I said a moment ago, that you move the piston so fast that no single molecule hits the wall, then you know that, that there's no work done on the piston, and the change in the energy is absolutely zero. If the change in energy is zero, but the volume is changed. So you can learn some things about that situation. You can work out some things about it. You can figure out what the final temperature is. It's solvable. But if you were to have squeezed the gas suddenly, then all kinds of very complicated things happen.
But going out, if you do it going out suddenly, the system is not in equilibrium, but the system will return to equilibrium, which it acts in a kind of potential energy that gets turned into kinetic energy as the molecules fill up that space.
Yeah, but the question is, what temperature does it return to equilibrium at? And that can be a very, very complicated problem. Not easy. Sometimes, once in a while, it's easy.
Question?
Yeah.
I'm confused about something in your derivation.
Of which?
T and V are the independent variables, E and S are the
Yeah.
dependent functions, if you will, of those independent variables.
Yeah.
So if you've got two independent variables, T and V, I don't even kind of know, what does delta T over delta V even mean?
This one?
Yeah, what does that mean for two independent variables to talk about delta T over delta V?
This was delta V and delta T, given that you are moving along a line of constant entropy. Okay? That's what we used here. We calculated delta T by delta V along a line of constant entropy by saying ds equals 0. Yeah.
Well, you can think of that as just as a constraint,
As a what?
Yeah.
a constraint.
Yeah. Right.
Can I ask a question, please? When we say slowly, is there a physical parameter that has to be less than or more than or something that defines slowly?
Of course. That itself may depend on the details. But, you know, roughly speaking, it means many, many molecules have collided with the wall so that you can average over the details of the molecular collisions with the wall. So, you know, we could examine specific cases, and some questions have very, very general answers. Some questions depend on the details. The question of exactly what time scales constitute slow can be one that depends on the details. The question of what happens if you move sufficiently slowly does not depend on the details. Yeah, so these are good questions, and but let's do what we can. And all right, so there we are. T, derivative of log z with respect to the volume at constant temperature. Now, when we work with the partition function up there, of course we fix the temperature. We say what beta is. So typically, when you calculate a partition function, it is the partition function as a function of other variables at fixed temperature. You worked it out at fixed temperature. Let's go back to the partition function for the ideal gas. This is going to be very easy from this point on. Here's the ideal gas. And the partition function was an integral. I'll just remind you what it was. It was an integral over all the x's and all the p's of e to the minus beta times the energy, which was p squared over 2m, right? And I'm not going to write it in great detail. This was an integral over how many x's are there? 3n. And how many p's? 3n. All right. Now, if you remember, this factored. The p integration doesn't depend on x at all. And the x integration just gives you what? If there was only one particle, it would give you the volume. And if there are n particles, it gives you the volume to the nth power. So this volume to the nth power times an integral which depends on the temperature but not on the volume. The P integration does not depend on the volume. So there's whatever was here, some function of beta. The reason it doesn't, and we either may or may not stick in the factor of n factorial in the denominator, that doesn't make any difference. Why? Because we're going to wind up, and this factor doesn't make any difference. The reason is because we have to calculate logarithm of z, and logarithm of z is going to be a sum of two terms. All right, so let's work out the logarithm of z. This is z. Log of z equals n log v from v to the n. And then there's a term that's constant. It depends on the number of particles, but it doesn't depend on the volume. We can put it down here, minus log n factorial. And then there's something here which is plus log of function of beta, beta being the inverse temperature. Only one term here depends on the volume, and it's this one. The one that just came from the fact that we had to integrate the position of the particle over the whole volume. Nothing else depends on the volume. So when we differentiate with respect to the volume, we can forget everything else. Plus uninteresting stuff. Okay, what is the derivative of the log? What is the derivative of the log of z with respect to the volume? Is equal to n, derivative of log v with respect to v? 1 over v, right? Over v. Now, we're supposed to multiply that by the temperature. And what do we get? We get the pressure. You recognize that? PV equals NT.
In this case, isn't n the number of identical?
Number of particles.
Well, when we started off defining this, we said that we were going to duplicate our container or our system.
We've done that. We're finished with that. That was just a trick to calculate the Boltzmann distribution.
Okay, so now n has changed definition.
Yeah. The ideal, right, it's just the number of particles. Okay, right. Notice that n over v is the density. N over v is not some crazy thing. So what does it say? It says, we can write it in various ways. You can write it pressure times volume equals n, the number of particles in the sample, times T. Now, you may be used to seeing this as PV equals nKT, where K is the Boltzmann constant. And of course, there is a Boltzmann constant here if you work in laboratory units. Or you can divide by n and write that P times the density of particles, the number of particles per unit volume, is equal to the temperature.
1 over rho.
Yeah, you,
Did I? Yeah. I'm sorry. They want to divide by the volume, not by n. P equals n divided by v, which is rho, times temperature. Density times temperature equals volume. Factor of Boltzmann constant, but we're grown-ups, so we are used to throwing away Boltzmann constant. This is the equation of state of an ideal gas. So it is exactly what you would have computed if you would have just used the intuitive picture of molecules bouncing off the wall. But here it's justified. And more than that, there's power in this method. anytime you can do the integrals necessary to calculate the partition function, you have a precise way of calculating. So this was just the simplest of many, many examples where people can calculate. Here we did it in order to see how the basic concepts fit together. This is how the basic concepts fit together. And that's it. That's the ideal gas. We're finished early today, so we can go back over it if there are questions. I think I was fairly clear tonight, but if not...
I think you had mentioned you were going to cover fluctuations.
Cover what?
Fluctuations?
Oh, okay. Well, okay. Yeah, all right, we have some time. Let's do fluctuations. I didn't bring any notes for it, so we have to wing it. Okay. What is a fluctuation? If you look in a box of gas like this, and it's in equilibrium with another system, so that it's exchanging energy with it, the energy won't be a definite value. The thing we've been calling energy is the average energy. The energy will fluctuate. Okay? The fact that the energy fluctuates in certain ways is evidence that the system is really made up of molecules and so forth. But we have to come to we need a definition of the fluctuation of a quantity when you have a probability distribution. Okay, so the standard definition, let's begin with a quantity whose average is 0. Okay. Begin with a quantity whose average is 0. That means the probability distribution for it, well, it doesn't literally mean, it doesn't necessarily mean that it's centered in any sense at the origin, but the average is 0. That doesn't look like a 0 average, does it? Okay. All right. The definition of the fluctuation, and it's not a complete description of the probability distribution. It's just a description of one aspect of it, which is kind of an approximation to its width. The average, let's just call this quantity x. The average of x is 0. That's not telling us anything. We knew the average was 0 because we set it up that way. But the average of x squared is not 0. Why not? Because x squared is never 0. It's positive on this side, it's positive on this side. And the average of x squared is a measure of the width of the distribution. So the fluctuation, usually called delta x, the uncertainty in x, or whatever we like to call it, is the square root of the average. Did we use this symbol for average? X squared. Or, let's get rid of the square root. The mean squared fluctuation is the average of x squared. Okay, now let's suppose that it's not centered at 0. So that the average is not 0. All we have to do is shift the variable so that the average does become 0 and do the same thing. In other words, we define a new variable called x minus the average of x. What's the average of x minus the average of x? 0. Prove that. There's something to prove. Prove that the average of this quantity here is 0. Okay? It's something you should prove. All right, so now we have something, a new quantity, which has just been shifted so that its average is 0. And what's the fluctuation in it? The fluctuation in it is the square, is the average of the square of this thing. So we want to take this thing, we want to square it, and we want to average the whole thing. It's good, it's a good quantity. Okay. let's calculate. Let's see what we can do with it. Let's see if we can make some sense out of it. First of all, we square before we average. So we're averaging x squared minus twice x times the average of x plus average of x squared. And we want to average the whole thing. Now the average of x squared, that's just a number. That's a number. It depends on the probability distribution, but it's just a number. What is the average of the average of x squared? It's just equal to itself. It's just the average of x squared. The average of an yeah. The average of an average is just the average. Okay, so this is just the average of x squared. What about this one here?
Same thing.
Not quite. Minus 2 times the same thing. Okay? So the average, if I average this quantity here, it will be minus 2 times the average of x squared. And what about this one?
It is what it is.
It is what it is, but it is not this thing. Why not? It's not the square of the average. This is the square of the average. It's the average of the square. So this is average of x squared. Minus twice this plus 1 times that is minus average of x squared. That's called the fluctuation, or I don't know, does it have another name? Is there another name for this thing?
Yeah.
The variance, yeah, the variance. Right. This is called the variance, well, but what it means is it's the fluctuation away from the norm, away from the average. All right, so let's keep that in our bag of tricks, that the uncertainty in x, or the fluctuation in x, the square of it, is by definition the average of the square minus the square of the average. Now let's see if we can calculate the fluctuation in the energy. We'll calculate the fluctuation in the energy in terms of the partition function. What do we have? We're armed with one quantity. Always one goes back to the partition function. It really does contain what you really, yeah.
I can't see that. That's delta x, and what's the superscript?
Squared.
Squared. It's just a definition. The left-hand side is a definition of the square of the fluctuation. You know, one might write that delta x is the square root of this thing, and talk about root mean squares and stuff like that. But this is definition. But what it does is it does measure the average. So what it measures is the width of the distribution, how broad the distribution is.
That is a name too.
Which?
The square root.
Probably called the root mean square or something.
No, the standard deviation.
Standard deviation, yeah.
And it's used in all the physics papers
Right.
you read about sigma.
Yeah, all that stuff is there. Right. But now we actually want to calculate. What it tells us is how much honest, real experimental fluctuation we expect in the measured quantity. How much will it vary when you measure it over and over again? Why does it vary? It varies because there's energy coming into and out of the system. It is really fluctuating. It's not just a mathematical definition. The energy in a box does fluctuate if it's in equilibrium with a bath, with a heat bath. Okay, so let's see if we can calculate it. We've already calculated, this is now we want to do the energy. We want to do energy. So let's apply this to energy. The uncertainty in the energy, the square of it, is the average of the energy squared minus the average of the energy squared. You see that these are not the same. What was the average of the energy? Do you remember in terms of the partition function? Minus d log z by d beta, right? Remember that? The average energy so we have the average energy already. We don't have to do any more work on that. But what about the average of the square of the energy? Let's go back to, first of all, what was the trick that we used to calculate the average energy? You remember? We said that the average energy is summation 1 over z e to the minus beta e sub I. And then we recognized that multiplying by e sub I here is the same as taking minus the derivative with respect to beta. So this is equal to 1 over z d by d beta with a minus sign of z. Z is the sum without the e, and d by d beta is the sum with the e. Okay. So this term we have under control. But suppose we want to get the average of the energy squared. What do we do? Average of the energy squared means the energy is squared here. We differentiate twice. We take a second derivative. Okay? Taking a second derivative, now we don't need a minus sign because when you differentiate twice, I think the minus sign will go away. You will get e squared times e to the minus beta e. So the average, this is the average of the squared energy, that's equal to 1 over z. Looks like it's the second derivative of z with respect to beta squared. Do I have that right? Help, do I have it right? Looks good, huh? And then minus minus, because it's squared, d log z, or let's just write it this way, 1 over z squared dz by d beta squared. So this is the fluctuation in the energy. Let's see if we can do anything with it. First of all, it tells us we can calculate the fluctuation if we know z. Again, it shows us the power of the partition function. All of statistical mechanics is about the power of the partition function and the power of differentiation. Okay, let's take a look at this. This sort of looks, let's see. Let's take a look at the following quantity. The second derivative with respect to beta squared of log z. Is that what I want? Yeah, let's take a look at that. Let's see what it is. All right, so it is, is that what I want? I'm not sure if that's what I want. d by d beta, let's see, d by d beta 1 over z dz by d beta. I think that's the same as this, is it not? Yeah. Yeah. This is the second derivative of log z. Here's the first derivative of log z, and then I differentiated it again. All right, let's focus on this thing over here. It has two terms. The first term is 1 over z. The first term is gotten by differentiating dz by d beta. That gives us 1 over z times the second derivative of z with respect to beta squared. And then what about the second term? The second term is obtained by differentiating the 1 over z times dz by d beta. What's the derivative of 1 over z with respect to beta? Minus 1 over z squared times dz by d beta. Exactly this. So we have an even simpler formula for the fluctuation. This is the fluctuation delta E squared. But yikes, this is even simpler. What is 1 over z dz by d beta? It is d log, but it's the average energy, isn't it? Or minus the average energy. This is minus the average energy. So here we have another formula that it's d by d beta of minus the average energy. Anybody know what this thing is?
Well, it tells you the slope goes down.
Hmm?
It tells you the slope goes down with temperature.
Well, it tells you how the energy changes with temperature. Beta is essentially, let's rewrite it. Let's write this as d by d temperature times d temperature by d beta. What's the temperature? Temperature is, what's it? The temperature is 1 over, beta is 1 over temperature squared, the other way around. Beta, temperature is 1 over beta. So what's the T by d beta? Beta, temperature is 1 over beta. The derivative is equal to minus 1 over beta squared. Is that right? Just minus 1 over beta squared? That's the T by d beta, which is temperature squared. Do I have that right? Yeah. So I think this is just temperature squared here. I don't have these things memorized, so I might be, I think that's right. Temperature squared, there was a minus sign, so the minus sign I think goes away. It's temperature squared times the derivative of temperature of energy with respect to temperature. Anybody know what the word is for the derivative of energy with respect to temperature? Specific heat. Specific heat is the question, how much do you have to change the energy to make a certain change in temperature? How much do you have to heat a bucket of water to change the temperature by 1 degree? This quantity, E, derivative of E with respect to T, is the specific heat. Do you know the symbol for specific heat?
C.
C. It's called C. It's not the speed of light.
Do you have to specify if you kept volume or pressure constant?
Capacity.
Here you're keeping fixed. Yeah, here, yes, you do. This is keeping the volume fixed. Yeah, we're keeping the system fixed. We're not varying the control parameter here in this derivation. So right. So this is the this is the specific heat at constant volume. In general, constant control parameters. So it's C sub V. Well, the specific heat might be defined as by dividing by the total number of particles in the system or something. But what this is the rate of change of the energy with respect to temperature. This is a famous formula. I think it may be due to Einstein, I'm not sure. Einstein and Gibbs, and I don't know who, it's probably Einstein, oh, and Gibbs. So the fluctuation in energy, if you know the specific heat, you multiply it by the temperature squared, and that will tell you how much fluctuation there is. Now, I left out something. I did leave out something. What I left out was the Boltzmann constant. I believe there's a K Boltzmann, I think the whole thing has one factor of K Boltzmann in front of it. With my definition, let's see, what was CV? CV was the derivative of energy with respect to temperature. But yeah, but I think there's from the change of variables here, I think there's a K downstairs and 2 powers of K upstairs. Yeah. So I think if you were working in laboratory units, I think this would have a K Boltzmann in front of it. That means it's small. Fluctuations are small. We expect fluctuations. You have a lot of particles. You expect the fluctuations to be fairly small. And that's where the smallness comes from. So this is the fluctuation in the energy of any system. This is not specific to any particular, this is specific heat, but it's not specific to any particular system. And so if you measure the specific heat as a function of, well, if you measure the specific heat, period, and you multiply by the temperature squared, and then you sit around measuring the energy in the sample, you should expect to see an energy fluctuation equal to this.
Does
So
it
why do
change
we-
if
why do we
pressure is
expect-
constant?
Why do we expect the specific heat to be a constant?
Constant with respect to what?
dEdt.
Sorry.
If you change, why would be dEdt?
Be constant? It's not constant. This is at this temperature. Yeah, CV is a function of temperature, and the fluctuations are a function of temperature. Yeah. No, it's not a function, right? So this is, again, part of the beautiful structure of statistical mechanics. This goes beyond thermodynamics. Whenever you actually see at the end of a formula like this a K Boltzmann, it's beyond statistical mechanics. It really does depend on the fact that the systems are made up out of molecules and so forth. It depends on Avogadro's number, essentially. K Boltzmann is closely related to Avogadro's number. So,
I have a question, please.
Yeah.
If you kept pressure constant instead of volume constant, and therefore you would perform work because it was moved, does this become different?
well, this was the derivation of the fluctuation of, no doubt, offhand, I don't remember the connections between all the specific heats, but yeah, you get the wrong answer if you use CP here.
Isn't the specific heat a constant for a given material?
Good. The thing that I'm calling the specific heat, I think is maybe not what would ordinarily be called. Normally the specific heat would be a constant, and it's per unit mass of the material or something. All right, so actually this would be the specific heat times, what's the definition of specific heat? It's the rate of change of energy per unit temperature per unit mass, for example, okay? So that means this specific heat over here is really the specific heat times the mass of the sample.
It's called heat capacity.
Good. It's called the heat capacity. Yes, that's the term I should have used. It's the heat capacity, but the heat capacity depends on the mass, the mass of material that you have. All right. So in other words, roughly speaking, this is proportional to the number of molecules in the sample. Okay. This is proportional to the number of molecules, how many, but it is the measured specific heat times the mass of the sample, or what is called the heat capacity, right? Yeah. Yeah, that's the word I should have used. Any other questions? Go home and look up heat capacities and so forth and see how big the fluctuations of a liter of water would be. And the important thing here, as I said, is that these formulas here don't depend on the details of what things are made out of. Once you measure the specific heat, you know the fluctuations without having to worry about what kind of material it is or anything else.
For more, please visit us at stanford.edu.